afternoon. Today we're going to just talk about radicals. We're going to just review a little bit about radicals. So for example, the square root of 4 is actually asking what number when multiplied by itself will give you 4. That's the question that they're actually asking you. We can call this a radical 4 or the square root of 4. When you have the square root of 4, in other words, it means the square root of 2 times 2. What number, when multiplied by itself, will it give you 4? 2 is the answer, because 2 times 2 equals 4. When we talk about perfect squares, again, this is a review of what we've been doing. Here are some of our perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and it goes on. I gave you a sheet that has perfect squares and the square roots of the perfect squares. It's very important that you become very familiar with all of these. I would go with the perfect squares all the way up from starting with 1 squared all the way up to 25 squared. You will find that it's beneficial to be familiar with those. So for example, the square root of some of the perfect squares are the square root of 1, which can be thought of as the square root of 1 times 1 is 1. The square root of 16 is the square root of 4 times 4, which is 4. And so on. The square root of 9 is the same, can be thought of as the square root of 3 times 3. The square root of 25 is the square root of 5 times 5. As you can see, under the square root sign, under the radical, if you see 2 of the same factors, 1 is brought outside. So keep that in mind for our next slide. Okay, again, keeping in mind what our perfect squares are, what I'd like you to do is take a look at what I have here, okay? What do you notice about the left side and the right side of each of these equations? Okay, for example, I have the square root of 18 equals 3 times the square root of 2. The square root of 8x squared is equal to 2x times the square root of 2. The square root of 32 equals 4 times the square root of 2. And we can also use the word radical. So radical 75 equals 5 radical 3. Sometimes you'll see that in higher math. And radical 45 equals 3 radical 5. That's kind of a simplified, shorter way to say it in math terms. So let's see, what are some of the things that you notice? All right, maybe this will help if I break it up even further. So let's just look at a few examples. The square root of 27. If I broke it up into factors under the radical sign, it could be the square root of 3 times 9. And then the answer becomes 3 square roots of 3. What I'm doing is I'm trying to find a simplified way to write a square root. We've been working with simplified from early on in your math career and math grades, starting with fractions, that you would always simplify fractions. So this is an example of where you need to, in the math world, be simplifying radicals, simplifying square roots. Okay, so the square root of 72. X squared can be simplified by looking at 72 and 2 factors of 36 and 2, which can be 6x, the square root of 2. And the same with the square root of 20 can be written as the square root of 4 times 5, which is simplified to 2 square roots of 5. One of the things that you might notice is that under the radical sign, you have some perfect squares, 9, 36, 4. And then what happens is the square root of each of those comes to the outside of the radical in your final answer. And here's another way of looking at this. One more way of looking at this, okay? Here's those 3 examples again. So the square root of 27 can be written as the square root of 3 times 9. And that can be written as 3 times 3 times 3. So, and then when I have 2 of the same factors under the radical sign, I bring out 1 to get 3 square roots of 3 as my final answer. Okay? The square root of 72x squared. I might think of it as 36 times 2. 36 is my perfect square, which is 6 times 6. My x squared is x times x. Every time you see 2 under the radical sign, 1 comes out. So hence, there's 6 times 6, 6 comes out, x times x comes out. What's left in there stays under the radical. So it's 6x radical 2. 6x square roots of 2 is another way of saying that. And the same with the square root of 20. That can be written as the factors of the square root of 5 times 4. And therefore, the square root of 5 times 2 times 2. I have two 2's, 1 goes out, and it becomes 2 times the square root of 5. All right? Let's look at some of these others right here. Let's look at the square root of 72 again. So 72, you may not have seen the factors right away that it's 36 times 2. You might see it as, well, I see it as 9 times 8. Okay? 9 is a perfect square, but 8 isn't. So let's talk about factoring it. What I'm doing is a factor tree to help me to get to simplify this radical. So 9 can be written as 3 times 3, and 8 can be written as 4 times 2. That 4 can be written as 2 times 2. And a shortened way, if you see it as two perfect squares, that you know that you can bring out a 2 and a 3, 2 times 3, which is 6, that is fine. You can stop right when you get some perfect squares. If you don't see it right away, every 2 that's on the inside, one of them goes on the outside. So what I have is, it's a 3 times a 2, and then I'm left with just this one, this 2, under the radical sign, okay? 3 times 2 can be simplified to 6 square roots of 2, which is the way we came up with it before when we had 36 times 2, which is another set of factors for 72. All right, let's look at 48. You may not recognize what 48 if there's a perfect square in there right away, but you might see it as 6 times 8. And then 6 has a 3 times 2, and 8 has a 4 times 2, okay? And then what I'm noticing that is that 4 has a 2 times 2. So every time you see a 2 of the same numbers, they go on the outside. So I have 2 2's here, and I also have these 2 2's right there, okay? So that means I can put out on the outside 2 times 2, okay? I also have 2 y's right there, so that is a y times a y, so I bring out one of them. And what's left is just, this 3 is left. So my final answer is going to be, for this one, I'm going to just erase this, is 6y square roots of 3. Okay, so that is a way to simplify. Let's look at 125 one more time, and it's m cubed. So what I have here is 25 times 5, and I have 3 m's. So I have m times m times m, okay? This is a perfect square, so I can immediately bring out the 5. I have 2 m's, I have 3 m's, and so I'm going to bring one of them out, and I'm left with a 5 on the inside and an m. Okay, so that is my simplified answer. Let's go and look at one more way that we're going to be using radicals. Just as a review again, the Pythagorean theorem for right triangles only. So we're going to combine these two items, square roots, and review these triangles that we've done before with the Pythagorean theorem. And we're going to combine those two. So the Pythagorean theorem says that for a right triangle only, that means I have a right angle in there, that the sum of the squares of the legs equals the square of the hypotenuse. And what's really important is the side that is across from the 90-degree angle is called the hypotenuse. It must always be across from the right angle. The other two sides are legs, and there's no particular order to those legs. So again, I can't emphasize enough that it must be for a right triangle only. This is what Pythagoras came up with. A squared plus b squared equals c squared, where a and b are legs, but c is the hypotenuse. So a and b are legs. So we can say that a and b are legs, and c must be the hypotenuse. Okay? So here it is right here. A and b are the legs, and c is the hypotenuse. So let's look at an example of why we would need to know radicals. So as I look, I say that my formula is a squared plus b squared equals c squared. I always write my formula first, and then a squared, I don't know what that is. I don't know what my a is, but my b is 4. So it's 4 squared equals c squared. Across from the hypotenuse is always, across from my 90 degrees, always my hypotenuse, which is what my 5 is. So I'm going to make that a 5 squared. Okay, and doing the math, a squared plus 16 equals 25. I subtract 16 from both sides. I have a squared equals 9. I take the square root of both sides, and a equals 3, because the square root of 9. So that is what my other leg is. This particular triangle, we have, when we take the square root, it's a nice whole number at the end. We came up with a perfect square for what our a squared is. But what we just learned before, not all square roots of numbers are going to be perfect squares. So here's an example where it's not a perfect square. So here, again, I have a right triangle. I need to know what this side is, this leg is. I'm given two other sides, so I may use the Pythagorean theorem. A squared plus b squared equals c squared. I don't know what my a is, so that stays a squared. I do know what my b is, which is 5 squared, and I know what my c is, which is 7 squared. So as I do my math, it's a squared plus 25 equals 49. I subtract 25 from both sides, and I get a squared equals 24. So now I take the square root of both sides, and look what I have. I have a equals the square root of 24, okay? What we've done in the past is we would put that into our calculator, and it's an irrational number, and it would go on. We'd have to round it. But now that we have learned, there is another way to simplify that answer, but keep it in radical form. So when I have that a equals the square root of 24, I'm going to look at a way to see if I can simplify it. So I might think of that this reminds me, one of the factors is 6 times 4. You can just go with what you originally think of. Okay? So as I do that, I see that 6 has 2 factors of 3 and 2, and 4 has 2 factors of 2 and 2. So what we say is every 2 that I see that I can bring out on the outside of the radical. So I have 2 2's, I bring 1 out, and what's left is the product of what's the 2 other factors that are left, which is 3 and 2. So it's 2 square roots of 6. So my simplified answer to what the missing leg in that triangle is, a equals 2 square roots of 6.